we are going to discuss the fixed charge problem, which is also referred to as the big M problem. In reality, there are many decisions that require fixed or lump sum costs. For example, in order to produce something, we might have to lease, rent, or purchase a piece of equipment. Or in order to produce a different type of product, we have to prepare or set up a new machine. Or to construct a new production line, we must set up a new machine or something like that, which will incur setup cost. For company, likely we have to hire some additional employees, which are considered as lump sum costs as well. Let us try to demonstrate how to set up a fixed charge problem through the following Remington manufacturing example. In this example, we have 3 products to produce: product 1, product 2, and product 3. We have 3 departments: machining department, grinding department, and assembly department. For each department, we have 600 available hours in total for machining, 300 for grinding, and 400 for assembly. In order to produce product 1, we need 2 hours of machining department, 6 hours of grinding, and 5 hours of assembly. We need 3 hours for product 2 from machining department, 3 hours from grinding department, and 6 hours from assembly department. For product 3, we need 6 hours from machining, 4 hours from grinding, and 2 hours from assembly. For each product, we have $48, $55, and $50 marginal profit for each product. At the same time, in order to produce product 1, product 2, and product 3, we must set up the machine. In order to set up the machine, we are going to incur a setup cost of $1,000 for product 1, $800 for product 2, and $900 for product 3. Suppose we do not have to consider the setup cost. In other words, we already have the machine set up, and we can produce as much as we want for all those 3 products. In that case, we can easily set up the LP model. Suppose Xi stands for the quantity of product I. In that case, we are going to maximize the total profit equal to 48 times X1 plus 55 times X2 plus 50 times X3. Subject to the constraints, for machining department, we are going to have 2x1 plus 3x2 plus 6x3 less or equal 600. For grinding department, we have 6x1 plus 3x2 plus 4x3 less or equal 300. For assembly department, we are going to have 5x1 plus 6x2 plus 2x3 less or equal 400. Of course, we are going to have the non-negative constraint xi larger or equal to 0 for all I equal to 1, 2, 3. But now, suppose we have the setup cost. We must set up the machine before we can produce a specific type of product. So what will be the new objective function? What are the new decision variables? As we know, we already have the decision variables xi equal to the amount of the product I to be produced. But in order to express the meaning of whether or not to set up the machine to produce product I, we must have a new decision variables. In this case, we are going to use yi. If we are going to produce some positive number of product I, in other words, xi larger than 0, then yi must be equal to 1. It means we are going to set up the machine. But if xi equal to 0, we don't need to produce anything, and definitely we don't want to set up the machine, because once we set up the machine, we are going to incur the setup cost. With the new decision variables, we can redefine the objective function. Again, we are going to maximize the total profit. Differently from the previous objective function, we are going to minus the setup cost. In this case, we are going to minus 1000 times y1 minus 800 times y2 minus 900 y3. If y1 equal to 1, it means we set up the machine to produce product 1, so that we incur 1000 setup cost. But if y1 equal to 0, we don't set up the machine, we don't incur the setup cost. The same applies to product 2 and product 3. We continue to have the constraints for those 3 departments. For example, for machining department, we have 2x1 plus 3x2 plus 6x3 less or equal 600. For grinding, we have 6x1 plus 3x2 plus 4x3 less or equal 300. And we have 5x1 plus 6x2 plus 2x3 less or equal 400 for assembly. We already defined yi will be equal to 0 or 1, so yi is a binary decision variable. And we continue to have the non-negative constraints. But right now, we kind of miss something. We have not defined anything to link how much we are going to produce for each product to whether or not we are going to set up the machine to produce product I. So we must find such a missing link. In this case, we are going to start with yi equal to 1 if xi larger than 0, or yi equal to 0 if xi equal to 0. That's the initial definition of yi. But let's try to look from another perspective. I'm going to rewrite yi equal to 1 if xi less or equal infinity. If we can produce yi to infinity, basically it means we can produce xi. This is very similar to the meaning of xi larger than 0 because we already have the non-negative constraint. If xi less or equal 0, definitely we are going to set yi equal to 0, which means we don't want to set up the machine. But typically, we don't need infinity in the model. So we are going to replace infinity with a big number we call big M. In this case, we have xi less or equal mi. Big M is a very big number. It's big enough so that we don't have to worry about how much we are going to produce product 1, product 2, or product 3. So in this case, we have yi equal to 1 if xi less or equal mi times 1, or yi equal to 0 if xi less or equal mi times 0. We can combine these two equations into one so that we have xi less or equal mi times yi. For all those 3 products, we can have 3 equations. For product 1, we have x1 less or equal m1 times y1. We can also rewrite it as x1 minus m1 times y1 less or equal 0. Similarly, for product 2, we have x2 less or equal m2 times y2. For product 3, we have x3 less or equal m3 times y3. Of course, in order to use Excel solver, we had better to move all the decision variables to the left-hand side. So we have x2 minus m2 times y2 less or equal 0, and x3 minus m3 times y3 less or equal 0. We know that if we have these three equations, if xi larger than 0, y1 must be equal to 1. But if we set yi equal to 0, because we don't want to incur the setup cost, the solver will give us y1 equal to 0. So basically, the mi will give us an upper bound for xi. And we know that we definitely do not want to have a very big m, because the bigger the m is, the longer computation time we are going to incur. So we try to find the least value for the mi so that we can solve the problem a little bit more quickly. So we try to utilize the three constraints we already have. Again, coming back to the three constraints for the machining department, grinding department, and assembly department. We try to utilize these three constraints to find the upper bound for the mi. For example, for m1, we are going to set x3 and x2 equal to 0. So coming back to the machining department, if x2 and x3 equal to 0s, the highest value for x1 will be equal to 600 over 2. So we get 300 as the upper bound for x1. Right now, if we look at the grinding department, given that x2 and x3 will be 0, the upper bound for x1 will be 300 over 6, which gives us 50. Looking at the assembly department, we have the upper bound of x1 will be equal to 400 over 5, so that we have 80. Among all these three numbers, we just need to take the least value of them so that we have 50 as the new upper bound of x1. And we just need to set m1 equal to 50. We can use the same approach to figure out the m2 and m3 for x2 and x3. Sometimes we get lucky, the problem will give us some capacity information so that we can directly set the capacity as the number of the big M. In summary, solving through this example, we have an objective function of 48 times x1 plus 55 times x2 plus 50 times x3 minus the setup cost of 1000 times y1 minus 800 times y2 minus 900 times y3. We have those three constraints for the machining department, grinding department, and assembly department. At the same time, we have the three linking constraints, which are x1 minus 50 times y1 less or equal 0, x2 minus 67 times y2 less or equal 0, and x3 minus 75 y3 less or equal 0. We do have the non-negative constraint, but at the same time, we have the yi must be binary decision variables. So to solve these integer programming models in the Excel solver, in addition to all those traditional constraints, you need to specify that yi must be binary. In the Excel solver, that is bin. So you just specify that yi must be binary and solve the problem like you solve a typical LP model, and you are going to get the optimal solution for this integer programming model. Thank you.